Hello, welcome back to Fat Mama Physics. This is the last video in the series, topic D1 on gravitational fields, with featuring our mascots Little Pig and Shin, our beloved singer, and featured in one song in one of my parodies. This video is going to bring all those big concepts together. Gravitational force, gravitational potential energy, gravitational field, and gravitational potential. The concept of this mind map is good for studying purposes. I actually encourage you to try to make or to complete this map yourself, and seeing how I've intentionally put these words in those places so they can be better linked to the ones that are beside them, adjacent to them. So if you don't want to be spoiled by this video, feel free to try that yourself, which I highly recommend. And if you do end up watching this video, try to retrace back these concepts again, or redrawing the mind map yourself on another sheet of paper and actually work out the connections yourself for that repetition, or just to go through those big concepts again. If you choose to watch the video and not try it out yourself, then bear with me. This might take a bit of time, and of course I probably will forget small details here and there, and you may even complete the entirety of this map on your own. Starting off with gravitational force, I'm going to just plop down their equations first with some mention of their definition. The gravitational force, this is Newton's universal law of gravitation, which dictates the attraction of two masses of a distance r away from their center of masses. Then we talked about, so before topic D1, before we talked about these big concepts in our circular motion, or tied to our circular motion, we talked about gravitational force as well as the gravitational field. The gravitational field is the gravitational force per unit mass, which boils down to big G, big M over R squared, in which big M is our point mass and this small m is our test mass. The new concept learned in this topic include gravitational potential energy, which is the work done when bringing an object from infinity to a space r from the center of mass of our point mass, big M. So EP is technically a work done, and so units of joules. And you know what? I forgot to put the units in the other areas, which we've talked about previously, so I forgot. Newtons, and then gravitational field. This is either Newton per kilogram, or we've used meters per second squared. Gravitational potential energy and gravitational potential relies on the fact that we redefine where the reference point is. Normally, we thought about the reference point as as the surface of the Earth. We changed it to being at infinity, where the gravitational potential energy is zero. Same thing with the gravitational potential. Is similar to that as well, in which it is also defined as zero at infinity. This is measured in joules per kilogram. One of the first things that I want to emphasize in this video is one key wording in terms of definitions. This is applied to when we go from gravitational force to gravitational field, and for gravitational potential energy to gravitational potential, and that's the concept of the per unit mass. Gravitational force is your force per unit mass, while gravitational potential energy is work done per unit mass. And this is where the kilogram to the -1, or kilogram to the -1, or per kilogram comes into the units. The purpose of taking something for its unit mass is we are now no longer interested in how big that test mass is. It can be as big or as big or as small as you want. It normalizes for all the potential masses that can be placed in any gravitational field or near any planet, star, or galaxy. So in terms of the equations themselves, you might notice that if we canceled out an m, the test mass m, then that gives us our gravitational field from the gravitational force equation, and then EP, gravitational potential energy, to just potential, one of the small masses goes away. Now we want to look at the top two, gravitational force and gravitational potential energy. I believe this probably was the first video that came out. We talked about how gravitational potential energy is related to the gravitational force. And because the gravitational potential energy is work done per unit, is the work done, we know that if we take the work and sum it up over space as you're moving your object, then the sum of all those individual forces times their individual displacements is going to give you the total amount of work. And the reason why we do that for Fg is because Fg is not constant as you move toward or away a point mass. In fact, you have an inverse square relationship, so that any time you want to find the work done is going to change as you move towards or away. And therefore, this is why the calculus is important. Calculus doesn't matter what the function is or whatever, it'll just take the area underneath the graph. So if you're thinking, oh, well, isn't it you just take the force and then you multiply by r, or the distance or whatever, and you know what, empirically it kind of looks like you can do that, because if I just multiplied this by r, it looks like I get rid of that r, one of the squares here on the bottom. Here, I'll write it out so you can see. So that kind of, it looks like it gets rid of one of those r's, but don't forget there's that negative sign, and this is why the doing it properly through calculus is important in terms of definition. So don't do it this way. This is like the cheaty shortcut way. And don't forget, this equation also assumes the fact that the force is always constant, or you have some sort of average going on, which is not very easily done with Fg. So you do need to sum up all the individual parts of that graph to get the area underneath this graph. So the link between here is summing up the work done by a changing force over space. So that's the link between gravitational force. I wrote down, you sum up all this individual area here. This is area underneath the graph. Area underneath Fg versus r graph. Now, if you're thinking about this, good for you if you're doing it. If you are thinking about, oh, well, if we go backwards, does that mean you have to take the slope then of your gravitational potential energy graph? So on what I mean by that is, if you have here's your EP graph, and we know it's an inverse, but it's below the x-axis. So then if you take the slope here, do you then get your gravitational force? By definition, yes. And there's also a negative sign involved. Anyways, the topic D1 does not focus on this, so I wouldn't actually put a lot of emphasis on this. But yes, you are right. If you do take the slope on this graph, you would get the gravitational force. But the direction might depend on the context, so there might be a negative sign involved. And to show that this is not as significant in this chapter, I just put some big brackets around that, so that you know that yes, they are connected. It's great. We love it when things all make sense, but I wouldn't be really studying that specifically. Although sometimes IB throws a level 7 question. It's like, okay. Anyhow, I digress. The other link that I think is more important here has to do with is basically the crux of equipotential lines, which the link between gravitational field and gravitational potential. This is where we talked about the contour maps. In terms of the contour maps, we see that every time you increase by an incremental amount of elevation, which we created the analogy that elevation gain is similar to gravitational potential gain. And how spread apart those equipotential lines, don't forget every line, it represents the same gravitational potential. So the blue equipotential line, the green and the red, depending on how far away they are from each other, dictates the strength of the gravitational field. Meaning if they're close together, that means you're going to change your elevation very quickly, giving you a steeper slope. If they are further distance apart, the slope is much gentler, signifying that you have a lower gravitational field. We also associate a gravitational field to imagine if something was rolling off that, rolling off that hill, kind of like what Little Pig was doing in those videos, then the steeper hill will result in a higher acceleration and therefore higher gravitational field. So the link here is from gravitational potential to gravitational field, in which the slope on a VG versus R graph represents the gravitational field. Technically there's a negative sign, so negative dr over v times vg. There you go. Not super important at this point, but it has to do with directionality of the gravitational field. You can check back to those videos if you don't remember. And this is also one of the questions that we went over, and I said that'd be something good for you to practice on, in which you have VG and you have R and you have and you're trying to find the slope here. The slope gives you your gravitational field. That is something that you want to be able to do because, as you see, IB loves graph questions. Also, likewise, and maybe not as important as the first thing I mentioned, if we go the other way for you savvy people, that means if you take the area underneath your gravitational field equation graph, it gives you your gravitational potential, or your change in your gravitational potential, which sometimes could be relative to infinity depending on the situation. And again, I'm going to put brackets around here because I see this a lot less and probably not very much, but it doesn't mean that the connection is there. And if we zoom out, you'll also notice that in all of these equations, they all look very similar. There is a big G, there's a big M, some variation of the R's in there, but they're kind of all related to each other by these different concepts. One of the cool things to note is when we study electricity, we're going to see the same thing, but for electrostatic force between charges. There's going to be some differences between electrostatics and for gravitational, with gravitational fields, but there's a lot of similar concepts. So hopefully this video gave us some idea of how all of those concepts are connected to each other. And that concludes the video series on topic D1 gravitational fields. Before we go, I just want to give thanks to our mascots, Lulu Pig and Shenshen, for being good sports. Even though in our last video, Lulu Pig was off at infinity, hopefully one day Lulu Pig will be able to watch Shenshen's concerts in another galaxy or alternate universe. Otherwise, we wish you the best of luck with your studies. Thank you for watching and staying with us to the very end. Lulu Pig, Shinshin, and Fat Mama Physics, signing out.